Hello, welcome to our video on a wave phenomenon. In other words, the effects that waves have in the environment that we can see. Now, we usually think of waves as two-dimensional, like in the picture to the right here. However, we know from real-life experience that many waves are three-dimensional. I know this picture isn't amazing, but you should be able to tell what this is. This is a picture of waves breaking on a shore. Here's the shore, here's the ocean, here are the waves breaking. And notice that we can tell where each individual wave that looks like this is based on basically these kind of lines here. Now we know that these waves are three-dimensional because very clearly they, obviously if you've ever been to the beach, you know that they have some height to them. You know that these waves have, you know that the waves have some depth to them. It's not just one line of atoms breaking over you, it's many. They also have some width here, okay? So we can kind of trace the crest of each of these waves by looking at this picture right here. So here's one, here's another crest of another long wave, out like that. We've got another one here, another one here. We've even got one starting to form out here. So what I've drawn in with these red lines is something called a wave front. You can tell where each individual wave is by looking at the wave fronts. In this case, I've outlined the crest of each wave. What I've really done is I've linked together all the points along this line are all at the same phase. Now I know that the points along like this line and this line are at the same phase, but I'm talking about like kind of this one singular wave right here, not the next one behind it. All of these points are at the crest. They must all be in phase with one another. Now, I drew across the crest, but we could just as easily draw lines connecting all the troughs together. That would still be a wave front. So I just need you to recognize a wave front when you see one. Another example of a wave front might be something like this. Say you drop a stone in some calm, flat water. What you'll see is the stone will displace some of the water, so that's kind of like a trough, but then the water will come rushing back in and actually be above the surface of where it normally is. That would be the crest. Now those two spread out from the center, creating this ripple pattern shown here. You can see all the different wave fronts though. In this case, the lighter areas are the crests. So you've got this crest right here that was just created, and then we've got, let's see, this one here. And then you've got this one here. And again, the farther out they are, the longer ago they were created. And then you've got these that kind of go off the page going all the way out here. So this is another example of wave fronts. Now what if we wanted to look at some wave fronts and measure and get some measurable variables here? Well, the easiest one would be to find the wavelength. You know that wavelength is just the distance between two successive points that are in phase with each other, like a crest to a crest or a trough to a trough. So being able to identify wave fronts means it's very easy to identify the wavelength. That right there would be one wavelength. Okay, the distance between 2 points that are both at crests, so 2 points that are in phase with each other. So one wavelength in a picture like this, when you're looking at wave fronts, can be found by measuring the distance between crests or the distance between troughs. Okay, those are wave fronts. Now we use wave fronts, and we need to understand wave fronts so that we can understand one of the effects that we're going to talk about today, which is called diffraction. The idea behind diffraction comes from the ideas behind this principle that seems a little confusing at first. Every point on a wavefront can actually be treated like its own small point source of waves, meaning even though the waves might have started at some other source, each point on a wavefront can be treated like here's a source of more waves that are going to spread out. Here's a source of more waves that are going to spread out. Here's a source of more waves that are going to spread out. That's how we can deal with them. The wave is always continuously spreading out in all directions from all points. The fact that we see crests and troughs has to do more with the fact with how the wave interacts with each other, how the waves coming from one particular point source interact with the waves from another particular point source. This idea that every point on the wave serves as the point source for future waves is known as Huygens' principle. Huygens was, I believe, Danish and lived a number of years ago, a couple hundred years ago. Now, this is a really interesting effect for wave fronts that are linear, that are parallel to each other. This means the waves continue to be aligned. So if you have waves that are parallel to each other, this is just an example with 4 little point sources. In reality, there's an infinite number of point sources around here. With these 4 point sources, we can imagine that the wave spreads out circularly from those in kind of concentric circles. Concentric means circles centered at the same point. So from this point right here, the wave that's spread out from this point is it's at this location. The wave that's spread out from this point is at this location, from here at this location, from here at this location. And obviously towards the side you see some kind of like some curves here, but look at the front. Look at the direction that the wave is traveling in, like right here. Look at how almost linear this is. Now imagine if we had infinitely more points. This would be literally a straight line right here. I can also show you this with a neat little app that I found one time. Here's what wavefronts look like spreading out from one singular source, obviously concentric, very circular. If I even put one other source in there, so 2 total sources, yeah, the wavefronts, now before they combine, obviously circular, but once they combine, I mean, on the sides, yeah, I can tell that it's curved, but look in the middle part, okay, kind of above the 2 sources. That wave actually starts to look fairly linear right about here, okay? I know that there's curved, but it looks more linear than this did. This was obviously circular. The combined wavefront here is kind of linear, okay? And as the waves continue to interfere, we keep getting that kind of linear spot. What if I have 3 point sources? That looks even more linear, okay? You can almost lay like a ruler across that and it would almost be flat, okay? And these point sources aren't going anywhere, so as the wave continues to propagate, we continue to get this fairly flat region in front of as far as the wavefronts go. Matter of fact, if I bring this all the way up to 10 point sources, and then bring this forward, I mean, look at that. You can, as it changes color, you can almost say that that's almost perfectly flat. I mean, we've got a perfectly flat region like right here, and right here, and here, 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 and here. And you could even actually probably measure the wavelength between, like, let's say here and here, these 2 wavefronts, okay? Obviously, to the sides, we're getting some stuff that's fairly curved, but right in front of these point sources, we're getting the point waves back, okay? We're getting those point waves back. And you can imagine that up at the top, that first wave that's created, I mean, if we consider all these points on the wave to be their own point sources, then we're going to keep getting the same thing. We're going to get this wave that just kind of self-propagates and continues to be planar. It continues to be aligned so that we get straight linear wavefronts. Okay? Even though each part of the wavefront is continuously creating new waves, those waves line up in such a way so that the wavefronts remain parallel. Now this has a neat effect if the wave happens to pass through a barrier with an opening. If the waves were to encounter a barrier with an opening, then obviously not every point source is going to continue through that barrier. Only the stuff in the middle, only the point sources in the middle are going to continue creating new waves. So it's like we went from that simulation having 10 point sources down to 3 or 4. The wave sort of stayed linear. The wavefronts were still sort of linear ahead of the wave, but to the sides of those point sources, it also started to spread out. So what actually ends up happening is we get this effect where the wave, even if it's planar or linear, wavefronts are kind of lined up like this going in. Once it passes through this barrier with the opening, the wave starts to bend. It spreads out to fill the space behind that barrier because there's no other wavefronts here to keep this linear. There's no other wave sources, I should say. Those got blocked by the barrier. Okay? So the wave spreads out like this behind the barrier. This is known as diffraction. The spreading of a wave behind or beyond a barrier. Now you've seen this in real life. You've seen this when on a clear sunny day, obviously there's a shadow that's created. However, that shadow is not as sharp as you might think it is. Okay, if you look really closely, there's not just a region of here's a shadow, here's no shadow. It's actually there's a grade to it. And that grade comes because of diffraction. Another example would be something like this. Oh, I gotta bring this down a little bit. Okay, another example would be something that looks kind of like, oops, this picture. And this hopefully is better on your paper than it is on this video. What we have here is a coastline, and we can see some wavefronts here, and I'm just being very general with these wavefronts, kind of coming in like this. We have two little barrier islands right here, and you can actually see from the picture that as the waves go through this opening between the barrier islands, they start to spread out like this. This fill the space behind the opening. Okay, that's a real life example of diffraction. If you go on Google Maps and find some sort of bay, I guarantee that you can find this. Okay, you can find this sort of thing. An example that's a little closer to home, if you go to the town park when the fountain is on, and it's kind of a clear, calm day, and there's no pond scum and algae to get in the way, then what you'll see as the water flows out from that little protected area around the fountain, there's a little opening in the retaining wall, you'll actually see this diffraction effect. You can actually see the ripples spread out beyond the opening. Think about how weird this is that this happens. I'm sitting in my classroom right now. If I take a tennis ball and I throw it out the door, I have every faith in the world that that tennis ball is not suddenly going to zoom off to the right or zoom off to the left after it passes through my doorway. Okay, it's a particle. It doesn't do that. However, a wave, in principle, would do that. That's what a wave does. It spreads out to fill the area beyond an opening. And I do just have to mention this real quick. The amount of diffraction is greatest if the opening in the barrier is small and if the opening is about the same size as the wavelength itself. Okay, so we see that for a small gap that is about on the order of the wave itself, there's more curving. The amount of diffraction is greater than if it's a large gap. Then you don't get as much. And I do just have to point out that my first year teaching, it takes about 30 seconds to talk about, but I did not talk about it because I thought that's too complex for the Regents. And I had a student who actually would have gotten a 100 on the Regents had they known that fact. They got it down, it was a multiple choice question, they got it down to the two most plausible answers. They unfortunately picked the wrong one, so that student got a 99. And I told them afterwards, I wish I had spent 30 seconds talking about this because they would have remembered it. Oh well, I apologize to that student. The last effect we're going to talk about on this video is known as the Doppler effect. And you know inherently what the Doppler effect is. You might not be able to put it into words yet, but you do know what it is. So I'm going to play for you a video that demonstrates this, and I'm going to play it twice. The first time I play it, I'm not going to show you the video. Okay, I want you to think about what the Doppler effect is and why this is happening. Here we go. Okay, so what happened there? Obviously, it's a siren. It's a fire engine siren alternating between two tones. And in the beginning, I bet you could guess that that fire engine is coming towards you. Not only is it getting louder, but at some point in the video, something happened, and suddenly the whole pitch changed. Okay, now let's watch it and see when the pitch changes. And this person's video is just absolutely terrible. But the sound is what's important. Okay, so what we're seeing there is that as the fire truck makes its way past your position, the pitch changes. Okay, When an ambulance or police car or fire truck is moving towards you, its siren sounds really high-pitched. However, once it's going away from you, the pitch or the frequency, the note or the tone changes. In this case, it decreases once it moves past you. And we want to know why this is. Okay? If you go back and watch that video, if you just Google Doppler effect siren, it'll come up. It's pretty clear. I think if I'm talking musically, it seems like almost a half step down, okay, between the two pitches. You can tell that something is different. And it's not just the volume, okay? Obviously, the volume is high when the truck is near us and lower when the truck is far away. Well, that's not what we're talking about, though. We're talking about the actual pitch. I have another animation to show you with this, but I won't show it to you just yet. Let's see here. Just want to reset that for once we're ready for it. Okay. In normal circumstances, we're going to be, so what I want you to do right now is kind of focus on this picture down here. In normal circumstances, if the source of sound is not moving relative to an observer, so something that's creating sound and something that's observing it, like a person, the wave fronts spread out in a circular form around the source. So you can think of a sound wave as having crests and troughs, just like every other type of wave. And they spread out concentrically from the source. Each circular wavefront has the same center, so we say that the waves are concentric. So there's the source. We have the wave fronts numbered 1, 2, 3, 4. You can imagine that they're all crests or all troughs or what have you. 1 was created the first, then 2, then 3, then 4 was created last because it's still nearest the source. We have two observers, A and B. Now the way A hears this sound is the sound waves are actually air pressure disturbances. They get picked up by your ear. In your ear, these air pressure disturbances, what happens is they wiggle this little bone in your inner ear, and that little bone sends signals to your brain, and your brain interprets the sound as either high-pitched or low-pitched, high volume or low volume. That's how hearing works. Sound waves always travel at the same speed if they're in the same material. Okay? Frequency has nothing to do with the speed of a sound wave. Wavelength has nothing to do with the speed of a sound wave. Or I should say, they don't control the speed of sound. The speed of sound depends only on the material the sound wave is going through. So if these sound waves are all going through air, they must all be moving at the same speed. All of these wave fronts representing, like this, let's say the crests of the sound wave, they're moving at the same speed, and we could measure the wavelength by looking at the distance between crests. If we do that, basically we could figure out the frequency. If we know the speed and we know the wavelength, we could figure out the frequency because we know that the speed is equal to the frequency multiplied by the wavelength. These waves, as they're created, have a certain distance between them. That's the wavelength. A is going to sense these waves hitting at a certain wavelength. The observer at A senses these waves hitting him at a certain amount per second, and A interprets that as a frequency. They perceive the same wavelength that the source gives off and the same frequency, and same thing for B. Okay? As the observer, your brain interprets the frequency, which is just the number of waves reaching you per second, as pitch. Now, if there were more waves hitting you per second, in other words, if there were more frequent crests, then the wavelength would be smaller and the frequency would therefore be higher. If the speed is never going to change unless we take this and put it in water or something, if the speed never changes and the wavelength goes down, then the frequency goes up. So if there's more waves hitting you per second, then that would be a higher pitch. However, what if we take that source and we move it towards either of the observers? So now we have observers C and D. This is a source moving at a constant velocity away from D and towards C. You can actually see with 1, 2, 3, 4 the location of the wave source when each of these waves was created. When 1 was created, it was here, 2 here, 3 here, and 4 here. The source is moving in the same direction as this part of the wavefront. So you can imagine the source is almost like trying to play catch up to these wavefronts. The wavefronts stay in front of it, but what's happening is because the source keeps moving, these wavefronts get squished together. Now, even if the source itself is creating the same, has the same pitch the whole time, the same frequency, and is creating waves, if it was stationary, it would be creating waves of constant frequency, constant wavelength. The source doesn't have to change their frequency, but because the wavefronts over here are squished, it seems to see like the wavelength is smaller. And it will seem as if the frequency is actually higher over here. Observer C perceives a shorter wavelength and a higher frequency, even though the frequency of the source has not changed. Observer D over here, see how the source was moving away from D? That means the wavefronts towards D are going to be more spread out. So since the wavefronts for D are more spread out, it seems like the wavelength is longer. And if the wavelength is longer and the speed is the same, then it's a lower frequency. D perceives a lower pitch. So it's weird that C perceives a high pitch, D perceives a low pitch. The frequency of the source has not changed, the pitch of the source hasn't changed, but all three of them are right from their own perspective. If there's relative motion between the source and observer, the observer will encounter wavefronts either at a bigger or smaller rate depending on whether the source is getting closer or farther away. If the source gets closer, the observer encounters more wavefronts per second. In other words, the frequency seems to go up, so the pitch seems higher. Likewise, if the source is moving away, less wavefronts are encountered per second, the frequency seems smaller, and therefore the pitch is lower. That's why, in the video, the fire truck seemed to have a lower pitch as it was going away, and a higher pitch when it was coming towards. The real pitch that it's producing is probably somewhere in the middle. Let me just show you the one application that I promised, the one little simulation. So this is, if there's no motion, we have frequency of 100 hertz up here, frequency of the observer. So basically the source has a certain frequency of 100 hertz. The observer hears a frequency of 100 hertz, or records a frequency of 100 hertz right here. If I pause this, and then I change the source position, let's just move it down here, and let's pause it again, and I'm going to make the source move towards the observer. So the source is moving towards the observer. Look how squished those wavefronts are in front. And then look at how spaced out the wavefronts are behind. Okay? As the source moves towards the observed frequency is higher. Once the source is moving away, the observed frequency is lower. So 500 as it's coming towards, 56 as it moves away. That's the basics of the Doppler effect. Okay? We don't have to use the Doppler effect with sound waves. We can actually use it with any type of wave. It especially works pretty well with light waves. There's lots of applications. By the way, this whole thing, if I didn't mention it before, is known as the Doppler effect. By the way, little kids understand the Doppler effect. Little kids driving around in the car with mom and dad, when they go and play with toy cars and they've seen like an ambulance or they've seen a fire truck, what sound do they make as they're kind of playing with it and moving it back and forth? They go, "Meow." They literally lower the pitch for their sound that they're making to imitate the car. They understand that the Doppler effect works. They can't put it into words. They don't know why it happens, but they did observe that it happens. So, anyways, we can use the Doppler effect in lots of different places. One of the ways we use it is we use it to predict weather patterns. Now, we use it to predict weather patterns because what we do is our instruments will actually send light waves, send light beams at cloud systems and storm systems, and when they come back, their frequency is slightly changed. We can determine which direction those cloud systems and storm systems are moving, so we can predict what the weather is going to be like. We can also use the Doppler effect to determine if light sources, such as stars and galaxies, are either moving towards us or away from us. And the way this works is the light waves, they have certain frequencies, and we can tell what the frequency is by the color. Light that has higher frequency would be like blue light. Blue lights have a typically higher frequency because they have smaller wavelengths than red light. Okay, so we are comparing blue and red light. Objects that move towards us and therefore seem to be emitting smaller wavelengths than they are, they tend their light, the word for it is spectrum. the total of all their light seems to be more blue than it would otherwise be. So objects that are coming towards us are said to be blue shifted. Objects that are moving away from us, therefore it seems like they have, the light has longer wavelengths and lower frequencies, it's said to be red shifted. Matter of fact, that's how we discovered that most objects in space, like far apart from our own galaxy, are moving away from us, okay? That the universe is expanding based on this Doppler effect, okay? Most things seem to be red shifted once you get past a certain point. This is also how a police officer's radar gun works, or a gun for determining how fast a baseball is pitched or a tennis serve is hit. Okay? Light bounces off the object that's moving, it returns with a different frequency, and therefore we can determine what the speed of the object was based on that shifted frequency. So that's it for wave phenomenon. What I really need you to get out of this is to recognize a wave front and understand what it means when you see one, that all the points on that front are in phase. I need you to understand that diffraction is a wave spreading into the opening beyond a barrier. And I need you to understand that the Doppler effect is the shifting of frequency due to relative motion. Objects coming towards you seem to be higher pitched, objects going away from you seem to be lower pitched. Okay? The next topic is interference, which is another phenomenon topic, but it needs its own video or two. I'll be back for that one later.